In 1967, a computer scientist was reading a 2,300-year-old Sanskrit text on grammar. He stopped at a particular section. Then he wrote a letter to the editors of the most influential journal in computer science. His proposal was simple. The most important notation in the history of computing, the system used to define every programming language, had the wrong name. It should be called the Panini-Backus form. Because the Indian grammarian Panini had built a system with striking structural parallels. 3,976 rules for generating all valid Sanskrit sentences. In the 4th century BCE, 2,300 years before computers existed. Every programming language ever written, C, Python, Java, JavaScript, is defined using a notation that has a structural parallel in a Sanskrit grammar text from ancient India. Modern programming languages are still formally specified using grammar systems descended from BNF. Large language models process language differently, but they operate on linguistic structures that formal language theory helped make precise. And in roughly the same historical era that Panini published his grammar, a philosopher in Athens published the first formal logic system in the West. Same type of structure, different continent, roughly the same era. This video maps both investigations and what they share with the system that defines every language a computer can understand. Human language is ambiguous. I saw the man with the telescope. Who had the telescope? Time flies like an arrow. Fruit flies like a banana. Two completely different meanings. Same words. Natural language works for humans because we carry enormous contextual knowledge. We resolve ambiguity unconsciously. A computer cannot do this. To execute a program, a computer must parse every instruction without ambiguity. Every statement must have exactly one valid interpretation. This requires a formal language, one where the rules of valid expression are stated precisely and every sentence either is or is not valid. Before 1959, there was no systematic notation for writing those rules down. Programming languages were described in informal prose. Different engineers read them differently. Compilers behaved inconsistently. The problem was not writing the language. The problem was describing the language precisely enough for a machine to understand. In 1959, John Backus, at IBM, presented a notation for describing the grammar of ALGOL, a new programming language being designed by an international committee of computer scientists. His notation used a simple structure. An abstract grammatical category on the left, a rule arrow in the middle, the valid expansions on the right. Like this, a sentence can be expanded into a noun phrase followed by a verb phrase. A noun phrase can be expanded into an article followed by a noun, and so on, until you reach the actual words. The following year, this notation was used in the official ALGOL 60 report. It became known as Backus-Naur Form, BNF. ALGOL strongly influenced the family tree from which C, C++, Java, Python, and most modern programming languages emerged. Most programming language specifications written since then use BNF, or a closely related formalism. Most modern language parsers are built around grammars expressed in BNF, or a direct descendant. What Ingerman noticed next is why some computer scientists still call Panini the first language engineer. In 1967, Peter Ingerman published a letter in the Communications of the ACM. He had been reading the Ashtadhyayi. His observation was precise. Panini's rules had striking structural parallels with Backus-Naur Form, the same use of abstract grammatical categories, the same type of production rules, the same capacity for recursion. Rules that refer to themselves. The same null symbol, what Panini called lopa, deletion, corresponding to the empty string in BNF. Ingerman proposed renaming the notation. Not the Backus-Naur form, the Panini-Backus form. This is where the mystery actually deepens. Modern formal language theory was developed independently of Panini. Noam Chomsky formalized generative grammar in 1956, without any knowledge of the Ashtadhyayi. John Backus developed BNF in 1959, also without knowledge of Panini. Ingerman's 1967 paper was a one-page letter, not a peer-reviewed study demonstrating equivalence. The structural parallel he noted is real, the line of influence is not documented. Modern formal language theory was developed independently. It converged with a structure Panini had already built. That is not a weakening of the story. That is the story. Two separate investigations, 2,300 years apart, arrived at the same formal structure with no documented connection between them. If you think that is coincidence, the next 20 minutes will give you a reason to reconsider. Before the Ashtadhyayi, notice something directly. You are thinking in language right now. The thought is structured. It has a grammar. It follows rules that allow certain combinations and prohibit others. Can you think a thought that has no grammatical structure? The rules that make language valid are also the rules that make thought communicable. Panini spent his life mapping those rules for Sanskrit, and in doing so, he may have mapped something more fundamental. Panini lived in Śālātura, a region in the northwest of the Indian subcontinent, in the area of modern-day Pakistan. Scholars date his work to approximately the 4th century BCE. The traditional dating places him earlier, around the 6th or 7th century. The scholarly debate is ongoing. What he produced is not debated. The Ashtadhyayi, the 8 chapters, contains 3,976 sutras. Each sutra is a rule. Together, the rules generate every grammatically valid form of Sanskrit from a minimal set of elements. This is not a description of Sanskrit, it is a generative grammar, a machine for producing valid Sanskrit from inputs. Several features of the Ashtadhyayi were not rediscovered in the West until the 20th century. What surprised later computer scientists was not one feature, it was 4. The first, the metalanguage. Panini did not describe Sanskrit in Sanskrit. He built a separate notational system, a metalanguage, to describe the object language. BNF does exactly the same thing. The notation describing a programming language is not itself that programming language. The second, recursion. Some of Panini's rules reference other rules. Those rules may reference the first rule again. The grammar loops back on itself to generate complex forms from simple elements. Every modern programming language uses recursive grammars. The third, the null symbol. Panini used a concept he called lopa, deletion. When a grammatical element is absent, lopa marks its absence explicitly. In BNF, the empty string epsilon does the same work. The fourth, the economy principle. Panini called it laghava. Every additional phoneme in a rule was considered costly. The shortest possible rule was always preferred, a preference for compact description. a value that later appears in several areas of mathematics and computer science. When Ingerman read the Ashtadhyayi in 1967, he was not reading a grammar of Sanskrit. He was reading a formal system with 4 features of modern formal language theory: metalanguage notation, recursion, null symbols, and an economy principle. Built 2,300 years before modern linguists formalized related ideas in mathematical language. His one-page letter was understated. Panini built a system for generating valid linguistic expressions. What happened next is statistically unlikely. In roughly the same historical era, on the opposite side of Eurasia, a philosopher in Athens was building a system for generating valid logical conclusions. He had no contact with Panini. There is no evidence either tradition influenced the other. His name was Aristotle. Aristotle's Prior Analytics, written in approximately 350 BCE, describes the syllogism: a formal rule system for reasoning. The structure is precise. All A are B, all B are C, therefore, all A are C. From 2 premises and a rule, a valid conclusion is generated. This is a production rule. The same structural type as Panini's sutras, the same structural type as BNF. Input: valid premises following defined forms. Rule: the inference structure. Output: a valid conclusion. Aristotle's syllogistic was foundational to Western formal logic for 2,000 years. From Euclid's geometry proofs to Boole's algebra 1847 to Frege's propositional calculus 1879 to the foundations of modern programming. The conceptual lineage from Aristotle's logic to a Python function is vast but foundational. 2 formal systems, one for generating valid linguistic expressions, one for generating valid logical conclusions, built independently on opposite ends of Eurasia in roughly the same historical era. And across 2,500 years, both structural types contributed to the formalism that defines every programming language and the formal language theory underlying how computers process text. Panini called the formal unit, sutra, a rule, 3,976 of them, generating all valid Sanskrit. Backus called it a production rule, written in BNF notation, generating all valid program statements. Aristotle called it a syllogistic form, a rule for valid inference, generating all valid logical conclusions. 3 names, 2,500 years, 1 recurring structure. A minimal set of formal rules that generates all valid outputs in a defined domain. Ingerman's 1967 proposal was never adopted. The notation is still called Backus-Naur Form. But many concepts central to formal language description, the notation every language designer uses, the grammar every parser is built around, have striking parallels with structures Panini formalized in the 4th century BCE. The notation kept the wrong name. The structure did not. The Vedic tradition did not view grammar as a technical subject. It was considered one of the 6 Vedangas, the limbs of the Veda, essential for understanding the sacred texts correctly. Grammar was the structure through which truth could be expressed. Without precise grammar, even a true statement could become false. A prayer mispronounced was worse than no prayer. Panini's project was not merely technical. It was the attempt to map the formal structure of valid expression itself. Consider this directly. Right now, you are thinking in language. The thought has structure, noun and verb, subject and object. The relationship between them follows rules you learned so early you cannot remember learning them. What would a thought look like without those rules? Panini spent his life asking, what are the minimal rules from which all valid expression arises? He arrived at 3,976. Every programming language designer, every linguist, every AI researcher is asking the same question. They have not yet found a simpler answer. In 1967, a computer scientist made a one-page proposal that was never formally adopted. The notation kept the name Backus-Naur Form. But the deeper question remained. How did a grammarian in northwest India in the 4th century BCE discover a formal structure that would reappear independently in linguistics, logic, and computer science across 2,500 years? Ingerman noticed the parallel. He had no answer for it. Neither does the field. Ancient wisdom, quantum mystery, direct knowing. The next investigation asks, what happens to the structure of language when you investigate the one who is using it? It is on your screen now and in the description.